Hello, my name is Michael Hotard, and I am going to go over proof 12.2 from Math 23A. And this week we're talking about manifolds, and it's really interesting that all the proofs actually build on each other in a little bit. However, I did find them a little confusing, especially this one. I thought that by the end I wasn't quite sure what we were trying to get, so I've restructured it a little bit, and hopefully that can help you out. We'll start off by just showing that our single variate knowledge of extremums and derivatives applies here. So if x naught is an extremum of gx and g prime x naught exists, then g prime x naught equals 0. So let's set gt equal to f of x naught plus t ei. Since f is a C1 function that's given to us, gt is differentiable. Let's apply the chain rule, and g prime 0 equals this here, and equals 0. So for all I, di f of x naught equals 0, and because this is true for all I, then we know d f of x naught equals 0, which is what we were trying to show, that this extension of our knowledge holds for the multivariate space. And there should be, those are vectors. That's what we were showing. For the next part, we're going to consider the function f and find out the interesting fact that we're ultimately trying to show. What we're going to get to is that the tangent space of a manifold is in the kernel of the derivative of f of c, where f is kind of constrained to be on the manifold. So, near the point c on the manifold, the n minus k passive variables are functions of active variables. And we can think of c equals a and b, where a are the passive variables and b are the active variables. So a is a function of b. Again, a is active, b is passive. And x is another set of active variables, y a set of passive variables for y near b. We're going to construct a graph function. So this is our g tilde, and we feed it in active variables, and we get a point on the manifold, x and y. So that's really interesting. This is actually a parameterization function. You can think about it that way. But we feed it in active variables, and then we are given back the g of y equals x and y. So point on the manifold. That's really cool. The graph function returns a point on the manifold. So now we know that f of g tilde y is on the manifold, and it has an unconstrained extremum at y equals b, because any choice of y leads to a point on the manifold. So this has kind of got way with our constrained extremum, which we didn't quite know how to deal with. Now we have an unconstrained extremum, which is, progress for sure. So what are we actually trying to show? Trying to show that the tangent space at point C on the manifold is in the kernel of the derivative of f at that point C. So what do we know about the tangent space at C? We know that CCM is the image of the derivative of the graph function. We can think about this. Remember, we showed that the tangent space is the image of the parameterization function, the graph function parameterization function. So the tangent space equals the derivative of the graph function at some point b, or given the active variables b. So this is actually at point c. What is the derivative of f at c? Well, let's think about how else we can write this. We know that the graph function of b is a point on the manifold, where it gives us the passive and active variables, and it's actually c. So this is a really cool relationship. The graph function of the active variables b gives us the point C on the manifold. So if we write the derivative of f of C, we can rewrite that as the derivative of f of g tilde b. This is where we're going. So let's consider f of g tilde b and apply the chain rule. So we have df g tilde b times dg tilde b equals 0. And we know this because we know that f of c is an extremum. So we're evaluating this at point C, which we showed, kind of plugging this into here. So what do we see here? We see the derivative of f of g tilde b times the derivative of g tilde b equals 0. And remember, this is just the chain rule applied to this. And let's do some substitution. And we get the derivative of f of c times the tangent space at point C on this manifold equals 0. Well, this looks like we have something multiplied by this matrix here, taking that matrix to 0. This thing is in the kernel. So we know that the tangent space at point C on the manifold is in the kernel of df of C. And just one important thing to note, there can be other vectors in the kernel of df at point C. This isn't necessarily the entirety of the kernel, but the tangent space at point C on the manifold is definitely in that kernel.